In today's class, we'll start looking at some RX architectures. So, if you remember, we looked at it very briefly in one class, maybe a month and a half back. So, we'll look at it in a little more detail in today and tomorrow's class. Okay? So, the first one we'll look at will be the direct conversion. So, last class we looked at direct conversion and heterodyne TX architectures. So, we'll look at the same thing for RX. Okay, so let's see what it looks like. So you have the antenna, of course. So you need a band pass filter to select the band. Then you have your LNA. Okay. Now, similar to last time, we'll also have the same. So far in the course, what we have been seeing is we have been looking at a very simple mixer, right? Even for receivers. But we saw last class that you can have modulation in both the I and the Q paths. So you need to do the same thing for the receiver, just like we used a sine and a cosine, okay, to in the transmit path to upconvert. We'll have to do the same thing in the receiver, because again you can have modulation in both the amplitude and the phase. Okay. Yes.
Last class you mentioned that the ion and the increased component and voltage component will be generated by the phase band.
Yes.
How they generated? How the phase band isolated to increase voltage component?
You can get it from the amplitude and the phase of the signal. Right? If you know the amplitude and the phase, you can A cos theta and A sin theta, A cos phi of t and A sin phi of t. Will give you. Yes, definitely. Usually what happens is it's not, computation doesn't happen that way. The what is produced is actually the I and the Q components. If you need to convert it to amplitude and phase, you will send it through a circuit called a codec. But the I and Q are directly this thing. I am not sure about how exactly they are produced in the baseband. That I am not sure. Okay. I can get back to you on that. I can find out and get back to you.
Because the input will be a single frequency signal, right?
No, it's a single frequency signal.
Not single frequency, band of frequency, but kind of band limited signal which is modulated by a single frequency.
Mm-hmm.
So output frequency you can expect it to shift to some other frequency.
No. Both the Xi of t and Xq of t are at the same frequency.
Yes.
Right? They just have different modulation. Well, they have independent modulation. Yes, that's right.
Yeah, that's exactly. I was confused. Like how do you generate the independent?
Okay, I can take a look at it and get back to you. I am not sure how exactly they do it in the baseband. Okay, I can get back to you. Yes. Well, it depends on the level of the interferers you can actually handle at the input. Okay, out of band interferers. If your LNA does not give enough, see, remember the LNA has a somewhat narrow band match at the input, but it will be limited. The amount, so you'll typically need to knock down signals by 40-50 dB, maybe higher. LNA will not give you that much. It will just help things along.
Typically, it's amplified.
Yes, it's not meant to be a filter. That's yeah. The output is the I and the Q. Okay, so let's just name the.
In this case, when we are doing direct conversion, does PLL doesn't step in case of direct conversion?
The PLL doesn't?
Then we don't define the PLL.
Of course you do. What generates sin omega LOT and cos omega LOT is the PLL. We'll look at that. I think If you have time, we'll briefly look at the PLL. I think many of the guys have already done it in the analog ICs course. Okay, so we may not get to the PLL. I think I'll probably skip it. We'll get to the oscillator though. Okay, we'll also look at ways to generate sine and cosine. That we can look at in class. Okay, how do you generate 0 and 90 degrees? We'll look at that in class. Okay, so this is A, and you already know what happens here. So this is B, this is C, and this is D. Okay, so what do you have at A? You have the, yes,
IMQ or in-phase and quadrature components.
in-phase and quadrature components at the baseband, going into the
How
baseband.
do we construct the original signal to get it back to our real?
How do you?
Finally, you will be you need to construct the original signal. Right?
Yes.
You will just add quadrature.
So what will happen is when once this goes in, this will go into your baseband. It will perform all kinds of digital processing, and then finally it will produce the voice signal. Because okay, in a typical system, right? If you take a typical cell phone system, this I and Q will have both voice and data. So typically, modern 3G systems, you can talk and browse at the same time, right? So both voice and data are encoded in the same signal. Okay, so the digital baseband has to separate out those two. Then that goes into the audio PA. Okay, so X of t, that is your received signal. Okay, so that is your received signal. We just use the polar form for now. So it's A of t cos omega LO t plus phi of t. I have written omega LO because omega RF is the same as omega LO. It's a direct conversion receiver. What do you have at B? Okay, so you have DC and a 2 omega LO component. Okay, so for now what we'll do is we'll assume that theta is 0. I'll tell you why we have theta there. Okay, so for now let's just assume theta is 0. Okay, that's what actually we have been assuming so far anyways. Okay, and at C, assume that after the low pass filter, right? So assume that theta is 0. Similarly at D, right, you'll have minus A of t. Sorry, C is? C before the low pass filter. I'm sorry. That's a mistake. Okay.
Quantity is Q of t or phi of Q of t?
It's phi of t. Phi is the is the phase angle. Yeah. Okay. Let me make it obvious. Okay. So how would you demodulate? Actually, you can do it very simply, because if you just want to extract the amplitude and the phase, it's actually very simple. So if you look at the signal at C and D, if you just do root of C square plus D squared, that gives you A of t. Right? Actually, what it gives you is A of t by 2, but yeah, you get the idea. And if you want the angle, then just have to do So you need to have the reason it's arctan 2 is the 4 quadrant tangent. You need to know, keep track of the signs of C and D. Okay, because otherwise you won't get a unique answer, right?
So why is that?
No, it's tan inverse, right? D over C.
As long as I have a two quadratic components,
Mm-hmm.
I can always find out the angle either using tan or using sine.
So to do that, you'll first, okay, so these two things you can do in parallel. If you do sine or cos, you'll need to do it in series, that's all. Okay. So then what you can do is, once you have the baseband signal, you can perform channel selection. Remember, you did band selection up front, you have received the full band, it's come down to the baseband. Now you need to select the particular channel you are operating in. On C and D. Okay. Of course, the other thing you can do is digitize C and D and do the channel selection in digital. You can do that also. Okay. Okay, so what does it look like in the frequency domain? I think we looked at this many times, but we'll just do it once more. So let's say this is your desired signal and you have some interferers around it. Okay. Okay, at B we're going to have this. Of course, you're going to have two components. Have this. Okay, so if you're going to do channel selection, you'll do it here on the desired signal. Okay, so let's look at a couple of other reasons why do we need I and Q. Okay, obviously the first reason we looked at is that you can have independent modulation on I and Q. Okay, so that is the first reason. Yes. It can be either. So one of the ways, okay, so if you choose polar based systems, then you can have information in the amplitude and the phase, you can split it that way. If you look at linear like QAM, right, I think we looked at QAM if you remember a long time ago. So the if you look at the modulation, right, it's called quadrature amplitude modulation. So it looks like this. So obviously these are best represented by an xy coordinate rather than r theta, right? Right. So obviously if the modulation is based on QAM or some such where it's easily represented using rectangular coordinates, you would use xi and xq, iq. Okay, whether it's the transmitter or the receiver. It's a different question how it's produced, but you would use it that way. Okay. Okay. What is the other reason? So normally we assume theta is 0. Okay. But in real cases, so what does theta represent? So theta represents, so we assume that the input angle was cos omega LOT. Okay. The LO is cos omega LOT plus theta. So it represents the phase difference between the local oscillator signal from the PLL, which you are generating to demodulate the signal, to down convert the signal, and the phase of the RF signal. Right? In general, it is arbitrary. Right? So let's take the example of an AM signal, in which case phi of t is 0. So x of t is just a of t cos omega LOT. Okay. What do you have at C and D? So you have a of t cos theta and a of t sin theta by 2. Okay, at each of these. Obviously, if it so happened that your local LO generated is at 90 degrees from your received signal, your I component, which is coming out at C, will be 0. Right? And if it's exactly in phase, the Q component will be 0. Okay. So what that means is, if you end up just using one channel, okay, there is a chance that you could get 0 output, depending on the phase. And you can never synchronize, really, because the received signal is what you are trying to demodulate, right? You can never synchronize it perfectly. Okay? Okay? Okay. Then let's consider the case of phase modulation, or FM, doesn't matter. You can't. It's arbitrary.
Theta varies depending on our input signal.
Yes.
And I have
Theta varying with input signal?
like synchronization will need to be done, right? Whatever RF signal you are receiving.
It is difficult, but because what you are receiving is only the RF signal,
Yes.
right? How would you don't know what phase information is there till you down convert it. And to down convert, you need something which is synchronized, which is impossible, right? You're trying to go around in circles. So you can never synchronize the two.
Okay. So theta is like how does it change? If my RF signal changes, does theta change?
Sure, of course. Theta is just arbitrary. Theta depends, for example, on the path it takes in the RF, on the RF side.
Okay. But thing is that finally when you do that square and add and the phase conversion,
Yes.
it doesn't matter, right?
It doesn't matter. That's right. And that's the whole idea. I'm trying to explain why you need that square and add. Okay, if you use just the I and Q channel, yes.
It's an inherent phase error which exists between my incoming signal and
Exactly. That's right. Now it's arbitrary. It's inherent and it's arbitrary. Right? You never know. So because
how good we are able to track that incoming signal. Once we are locked in,
once you are logged in the PLL, then you can try to track it. That's right. You can try. But there will always be some phase error associated between the two. Okay. So let's look at the FM signal. Yes.
The input signal we are assuming of a constant means particular frequency, then only we can define the phase of the input signal.
Okay. So you can assume it's sine and it will turn out to be the other way.
Then if RF frequency also I know, then I can always find a relation. Means mathematically I can find what the phase will be.
What do you mean? I don't understand.
Means whatever RF signal is coming, if I know the phase of that signal.
But how do you know the phase of that
at
signal?
RF frequency.
No, but how do you know the phase of that signal? You know the phase when it's being transmitted. You don't know the phase when you're receiving it.
By zero crossing or something like it.
No, because that will be extremely difficult, right? Calculate it just based on zero crossing. Yeah, that's going to be extremely difficult. Because see, if it is a pure sinusoid, you can do it based on zero crossing. If it is in general, if it's a modulated signal, you can never do it based on zero crossing. That's for sure. Okay. You have a cos phi of t at C. A sin phi of t. Okay. Suppose you take, now that it's only in phase, you may think that you can just use one of these. Let's assume even the theta problem is gone. Okay. What happens? Let's just take the case of C alone. Okay. Remember, what you get is this. Let's just take that as a reference, a cos phi of t. Okay. So the real signal could be one of two choices. You can never get it uniquely. Okay. And same thing with the sin phi of t. There are two portions of the quadrant, right, where it can have the same sign. Okay. So what are some of the advantages? We look at the advantages and disadvantages. Obviously, it's very simple. Okay, you don't have this multiple frequencies. You don't have second IF and so on. So very simple. Definitely. And one big thing which we know that heterodyne systems have the image problem, right? Where if your RF is omega LO minus omega IF, you have an image at omega LO plus omega IF, right? That's a fundamental problem. Here there is no image because the RF is its own image, because IF is 0. Okay. What else? As you can see, we didn't have to use these image reject filters, some extra stuff, right? So it's definitely very integrable because it's very simple, and you don't need very high quality filters. Except for no off-chip filters, except for band select. You always need that band select right after the antenna. Okay. Okay. So if you don't need an image reject filter, what does this mean? So remember that the image reject filter comes between the LNA and the mixer, right? So which means you don't have an insertion loss. You don't have, more importantly, the LNA does not need to drive 50 ohms. That is a big deal. Because remember, LNA burns a lot of power trying to drive 50 ohms. Okay. Okay. And of course, you need only a single PLL. That's a big deal, because in the case of the IF, you have one omega LO, and then to demodulate again at the baseband, you need a second, right, omega IF. Okay. So all of these look very good.
It's more sensitive to noise.
Why?
Higher frequencies.
Why is that? What kind of noise? You mean noise in the PLL or noise in the RF, incoming RF signal?
Because at this high frequency, we have more parasitics, so maybe performance is not that good.
Okay, so the typical IF frequency would be maybe 100, maximum would be like 100 megahertz, but it will typically be much lower. Okay, so the LO frequency itself would be around the same between the two, approximately the same. They won't be very different. Okay, so this RF PLL you will always need. In the other case, you will need a second PLL to demodulate again. at the baseband. Okay? Yes? Because the image rejection, okay, so typically the image will be, can be maybe 40-50 dB higher than your received signal. Okay, so if you need to knock it down, you need to knock it down by quite a lot to get your system working properly. Okay, and you can get that kind of performance only with off-chip filters. And remember, it also depends on your IF. We saw this before, right? There's an inherent trade-off between selectivity and sensitivity. So if you choose a very high IF, right? You can filter out the image reject filter is much easier to do. Okay, you can filter it out very well. So your sensitivity is very good because your image falls on top of the signal, and that's very good. But then what happens is, once your IF becomes very large, you do your channel selectivity in your baseband or in your IF, right? In the case of a heterodyne. When you do that at higher IFs, if you want to knock down the adjacent channels, that becomes tougher. Okay? Yes? Before and after? The? Yes, before and after the LNA. Well, no, definitely, yes. That is, it definitely helps with that. I would say the number one is the noise figure, but you can integrate part of it into your band select filter. Okay, but if your IF, image falls inside the band, then that's a problem. But apart from that, there is no particular reason why you can't do that. Okay, except for the noise figure part. Noise figure part is huge. Okay, that is a big problem. I can't think off the top of my head. I can't think of anything else. Non-linearity, why?
Because interference are there, which amplifier is non-linear.
No, but your LNA better be quite linear. I don't think at the signal levels we are talking about at the LNA, it shouldn't be a problem. Okay, because we are talking about microvolts, tens of microvolts.
IIP3 will be amplitude will go into if there are other signals with amplitudes, that will interfere, like that will reduce the gain of the actual signal. Like the gain reduction that happens due to the
Yes. Now that is possible. That always happens, irrespective of whether you put in the right. If you have adjacent channel, that could always happen. Okay. The assumption is the band, all the signals in the band, right? Yes, exactly. Because you want to get all of those things down, and you do the channel selection at the baseband. Okay. Okay. So what are the disadvantages?
Doing the channel selection in the baseband, we need to provide large dynamic range for the RX.
Large dynamic range for what? For what in the RX?
RX part, entire part, because when we digital domains,
So what? Actually, what you will see, we'll come to that. We are going to see that. It's a trade-off between dynamic range of the ADC and the analog path, rather than the overall RX. Okay. Most of it, there is a trade-off involved. The trade-off will be, we'll come to it. Let's come to it. Okay. Okay. The number one problem, DC offsets. Okay. So if you have any DC offset in your baseband, that is going to add directly with your signal. Okay. So okay. So what happens is, if you look at the signal coming in through the coming in at the output of the mixer, okay, that is what goes into your baseband, right? You have some baseband amplification, and then you have this, you have some filtering and so on. Okay, so the signal going in there will probably be a few hundred microvolts. So typically, if you see, most of the gain, right, comes from the baseband. Okay, you have some gain. What do you have in the RF? You have the LNA, you have the mixer. Okay, so the signal coming in is 1 microvolt. Signal coming in is probably a few hundred microvolts coming out of the mixer. Okay, and at that point is where you are adding all the input referred offset of the baseband. That will typically be in millivolts or tens of millivolts. Okay, so that is a big problem because your offset is going to be much larger than your signal at that point. Okay, so your RF gain. So typically, okay, what you need is your overall gain from your system will be maybe like 100 dB or so. Okay. And so most of your gain will be coming from the baseband. Your input referred offset could be in tens of millivolts. So what does this mean? So your DC offset could end up saturating your baseband amplifiers. Okay. Saturation means desensitization, right? We know that. We saw this before. The next one is LO self mixing. Right? We saw this before. So you can have your LO leak to your RF port or the input of the LNA. Yes. Yes, the difference is, okay, if you take the heterodyne architecture, okay, so the signal first goes down to IF, okay, at IF you don't care about the DC offsets, okay, but at that point on the IF stages you can add more gain, okay, so instead of being in, you can add another like 30-40 dB of gain in the IF, and then you have only 30-40 dB of gain in the baseband. By that time the signal is already large enough. Is that clear? So what do you have here? You again have DC offsets here. From your LO leakage. And remember that, so let me just put the antenna here. We talked about re-radiation, right, from the antenna. So what can happen is, so if you have some kind of reflection and it comes back and gets received again, you can have time varying DC offsets depending on the reflection paths. What else can you have? If you have, let's say at the output of the LNA, if you have large interferers, okay, those interferers can actually leak into the LO path. So you can have the reverse case. You can have leakage from RF to LO of the interferers, and then through the mixer again the interferers will mix with themselves to cause DCs. That can also happen. Okay, what else? So 1 over F noise is a big problem, right? Because now your signal is at baseband.
Does it mean what is the typical isolation numbers required between LO and RF?
Typical isolation numbers would be 50 dB, maybe higher, maybe lower, depending on, right? But not much, not very different. But it will be around 50 dB. One hour of noise of what? Of the mixer and your baseband. Those are the two things which matter the most. Okay. Remember in the transmitter we looked at LO pulling. right? You can have the same thing here. Okay. If you have leakage like this, right, the modulation on the leak on the leaked interferer can get passed on to the yellow. That can happen. So it depends on your RF to LO leakage. Okay, the other big one. So some of these are, can be showstoppers. Others are an annoyance, but things like LO pulling may not happen always. Okay, those kind of things may be in specific cases. But obviously DC offsets, 1 over F noise, they are all common to all direct conversion systems. Okay. The other thing, even order distortion. Now this is big. Okay. Yes.
1 by F noise is only the critical one because it's the low frequency component gets transmitted.
Well,
Modulated to high frequency or
so if you look at your signal, so let's say your signal looks like this in baseband. Okay. What does a 1 over F noise look like? It looks like this.
something like
Yeah, so basically it corrupts all the information in a major portion of the signal, low frequency portion, right? Okay. Very low. Okay, so let's see what happens if we have even order distortion in your system. Okay, let's look at the signals at A, B and C. So let's say we have an RF signal we want, and we have a couple of interferers nearby. Okay. Sorry. What do we have at B? So let's say the LNA has some even order distortion. So what happens? Remember, B is the output of the LNA. Okay. If it has a second order distortion, these two interferers will produce an omega 1 minus omega 2 component. And of course, you have your RF. Omega 1 and omega 2. Okay, this is the output of the LNA. And what you will have here, let me keep it by a, make this red. Okay. So any even order distortion, especially a second order distortion, can corrupt your signal. Mainly because, of course, so the thing is, what we are assuming here is, remember, if this normally goes through the mixer, this would actually get upconverted to some other frequency. But we are assuming that mixer has some limited RF to IF feed through. Okay, so all mixers will have limited, there will be some rejection. So it depends on the even order distortion. So what, okay, we'll come to that. So what do you, if you have even order distortion, you can represent the even order distortion of the system using something called IIP2, right? We looked at IIP3, which is the third order distortion. Similarly, second order distortion can be characterized through IIP2 of the system. Okay?
I didn't follow that.
Yes.
How how can megawatt minus omega to stay at that? You have to get modulated to sustain.
Yes, but then I'm assuming that you have
Oh, feed.
RF to IF feed through. Okay? So let's say now we want to improve your IIP2. How do you improve your IIP2? You want to remove, yeah, exactly. So the number one thing you want to remove your second order, fourth order and so on. So the best way to do that is go differential. Okay? Of course, the obvious problem with going differential is power consumption, right? Okay? And even if you go differential, finally your IIP2 is going to be limited by your matching. Okay? Matching between the differential paths. Okay? Then the other disadvantage, you can have IQ mismatches. So remember, we are relying on the sine and cosine of the LO and the matching between the I and Q paths to produce a half A of t cos phi of t and minus half A of t sin phi of t, okay, at the base bands. Obviously, if you have mismatches in the gain on the two paths, or if you have mismatches in the phase going into your mixer, sine and cosine, then that will corrupt your signal, and in the end it will affect your bit error rate. Okay?
It should be reversely.
Should be?
Should be anyway true, irrespective of what. As long as you have I and Q,
Yes.
you need to ensure that both are same.
Absolutely, that's right.
That will include amplitude and phase differences.
You can have IQ, you can have corruption due to both. Phase imbalance will come in from the LO path, amplitude imbalance will come in from the gain in the RF path. Okay? Okay. Channel selection. How do you do channel selection? So you have three options, right? So now you have the I and the Q signal. So you want to get some gain, definitely. Okay. So you want to do some filtering. Okay. And in the end you want to digitize it. So this is one option. Okay. The other option, so this is A. Do your filtering first. Do your amplification. There are, obviously different trade-offs associated with each. Okay. Third option, amplify. Okay. And do the channel selection in digital domain. Okay, as far as filtering itself goes, obviously C is the easiest because you can get very, very sharp filters, very good filtering in the digital domain. Okay, but what that means is what is coming into the ADC is actually the desired channel plus a bunch of other stuff which are other channels, adjacent channels, which can be much larger than your desired channel. Okay, so that means that your ADC needs to have a very good dynamic range. Right, it needs to resolve your signal in the presence of large interferers. So that is a trade-off in C. If you go to A and B, the ADC is a lot simpler, right? The dynamic range is only moderate, a few bits like between 4 to 5 bits, maybe 8 bits, worst case, is good enough. Okay, but then there is a trade-off between the filtering and the amplification. Okay, obviously if you have the filter up front, it adds noise definitely because it has a loss, so that's a problem. But once you cut down the interferers, your amplifier can be non-linear and you won't see a problem with that. If you do it this way, the amplifier needs to be very low noise and it has to be very linear. Okay, each one has its own trade-offs and its own problems. You are pushing the problem to one of the blocks, one or more of the blocks in each case.
We can have the block C, we can have an intermediate filter before ADC.
You can do that, yeah, you can always split the filter between, yeah. But the thing is, remember, we are talking about spacings of maybe a few hundred kilohertz to a few megahertz, and you need to knock down these interferers by 40-50 dB. That is going to be very difficult with an analog filter. Okay, if you want to get knock it down by this adequate amount, the filter has to be really, really good. That is definitely a problem. Okay.
Amplifier is a normal amplifier or it's an AGC amplifier?
It can be an AGC amplifier. It most probably will be an AGC. Okay. As in a VGA, not an AGC. It will be a variable gain amplifier. Okay. The gain itself, so the AGC comes in from the overall system. It won't come in from on the analog path. Okay. Okay. Now, how do you solve these problems? Let's look at DC offset. Obviously, the easiest way to do it is avoid transmitting any information in and around DC. That's obviously the easiest way out, right? That you can do. You can employ some kind of DC free coding. You can do that. But in many cases, you don't have a choice. Okay? So then what can you do? So you can try to get as close to DC as possible and do some kind of high pass filtering. Okay? Which means AC coupling. Okay? Now obviously, the lower you want to cut off, right? Which means you can transmit more information in the signal itself. The lower you go, the larger the capacitor. The larger the capacitor, you have settling time problems, so that's a big deal, right?
Use the low frequency content in the signal.
So what you can try to do is so you need to go really, really low if you want to do this. Okay? So your capacitors will become huge. That is another problem.
Settling time problem will come only if you talk about large signal.
Will only come?
Only if you talk about large signal. Like large signal at the oscillator.
No, because every time you are receiving, right, you need to set up the DCs on both sides. That itself will take a long time.
That's what I'm saying.
Yeah, of course.
Biasing has to be changed.
Yes, biasing has to change. So whenever that happens, there will be a long settling time.
For small signal, it will not be.
Small signal, it won't be a problem. Okay? You'll have huge caps. So that is. But in reality, what you will have to do is do some kind of DC offset correction, either in the baseband or otherwise. Okay, so that is definitely the best way out of it. And now that you have a very powerful digital, you can do all kinds of things. Okay, you can do it periodically. There are many techniques. Okay.
That's why it's calibration.
Yes. So it will be part of the calibration. Because typically your DC offset will be constant. Okay, it won't vary with time. At least the component from your circuit due to mismatches will not vary with time. Okay, so that you can use calibration. You can use analog techniques also, definitely. Okay. Flicker noise. Actually, before that, so obviously, if you want to do this kind of DC free coding, right, it is useful for wideband signals. So if you have signal content only in, let's say, a few kilohertz, doing DC free coding will cause a much larger loss of data rate than if you have already like a several hundred kilohertz or megahertz. So if you have, let's say you want to cut off in and around DC, let's say a couple of kilohertz. If your signal whole signal bandwidth is 10 kilohertz, it's a big deal, right? You're losing a lot of data rate. So signal bandwidth a few hundred kilohertz, you don't care too much. So that's an obvious trade-off. Okay. Flicker noise, of course, the only way to do it is increase the size of the signal, right? Sorry, increase the size of the devices, right? Increase device sizes. But obviously, the problem with this is the minute you increase device sizes, you'll need to burn more power to drive these devices. For example, if you increase the size of the mixer, you'll need to burn more power in the VCO path. Okay? Okay? What else can you do? If you have the choice, use bipolar. Okay? Bipolar transistors have lower flicker noise. But in this class, since we are concentrating on CMOS, we don't have a choice. But you can just remember that if you have, for example, like a BiCMOS process, or you have access to both, you can try to design some of the circuits in bipolar. That will definitely help. Okay? Yes?
Generally, this flicker noise is covered by input stage. And most of the time.
No, in this case, the input is at RF, right? We notice that flicker noise comes mainly from the mixer and the baseband, right?
So we employ some offset cancellation techniques.
Which one?
Offset cancellation techniques.
To help with flicker noise?
Yeah, like some clocking.
You can do, sure, that is, you can do that in the baseband. You can always do that. It's same thing. That's right. Okay, let's look at linearity. So, the main thing you want to improve is IIP2. And we already looked at this, right? Design differential circuits is the most obvious thing you can do. But be careful about symmetry. Okay? Then one last thing to be careful about is in your gain path. Remember, most of your gain, in the case of the heterodyne, you can split the gain between your RF and IF. In this case, you only have RF and baseband. Okay? So a major portion of the gain has to come. So there you have three places, RF, IF and baseband. Here it's just RF and baseband. So you will have a significant portion of the gain coming from the RF side. Okay? So what you have to be careful about are parasitic paths. Okay? Because the minute you have large gain, if you have parasitic feedback paths, you can have stability problems. Okay? Okay. Yes.
Feedback path is stability problem. That's the how jack is dependent on the gain.
Because the more gain you have, it's already yes, the loop gain will become larger. Okay. Okay. So we'll stop here and continue tomorrow. I think so. We are done with direct conversion systems. Okay. Does anybody have any other questions? So we move on to heterodyne systems and image reject receivers tomorrow. Heterodyne, we have already looked at it. Most of the basic trade-offs in previously. We'll just quickly go through it and then go on to the motivation for image IR receivers. Okay.